Right now, everything you see and everything you hear is being recorded. Won't be on Blackboard until probably sometime tomorrow, and in your playlist until I get that set up. So let's go back to and start off with the syllabus. And again, I haven't had a chance to update the syllabus, so this is set up for last spring, I think is when I had it set up. Yeah, last spring. So the hours are wrong. The content of the syllabus is still okay. It's just the little things like this. The class is now meeting Monday to Wednesday. That part's right. 2:30 until 5:25. Right? Did y'all see that? I put the message out there on Blackboard or somewhere. So 2:30 until 5:25, because summer is more compressed, so we have to meet longer. Actually, we're meeting too long, but that's a different story. That's our count between 2:55, so y'all are in the right place. My name is Charles Fowler. My office is in A265, which is, I'll show you how to get there from here. If you go out the door here, hang a left, and go down this half flight of stairs right there, go almost to the end of the hall. Don't go all the way to the end. The last office on the left, right before the stairwell, that's my office, 265. Okay? So pretty close. You can get there fairly easily. On Fridays, but there's only 2 Fridays left in this term because the months of June and July, we go to a 4-day work week, so we're only here Monday through Thursday. The college is closed Friday, Saturday, and Sunday. Okay? It's always closed on Sunday. And in fall and spring, we have Friday and Saturday classes, but in the summer, but to save on heat, cooling and stuff like that, so they close it Friday and Saturday. We don't have enough people signing up for courses on Friday and Saturday anyway, so they decided on to close it. Okay, but the 2 Fridays we have left, that's the day after tomorrow, and then the first Friday in August, that will still be in summer term. Y'all will be through by then, but it'll be in summer term. I'll be on the Birmingham West Campus, and that will be in the academic building, which is B122. So actually, Dr. Carl Pruitt, he's the Associate Dean. It's his office suite, and I'm in the copy room behind the secretary's desk, okay? But it's in room 122. Now, this number was the number for the phone that was in there, but that phone doesn't work anymore. It used to be the office for the grant coordinator for a couple of the grants, but she only worked 4 days a week, or 3 days, something like that. So I used it on Fridays. Well, the phone quit working, and I don't think works there anymore, so they just left it with no phone. And the phone that's in there doesn't work. So call 929-6377. That's the secretary's number. And like I said, I'm just right behind her desk in the copy room. So if she's not in, I try to pick up the phone for her. And if she is in, she'll call back and say, this is for you. Okay? So that's only for this coming Friday and the first Friday in August. My email address is still good, so you can email me anytime. Right now I'm pretty far behind in emails, but I'll try to catch those up. Let me go back to my phone here on this campus. I didn't mention that. 929-3449. Here's an issue. We were out for the break between, and I have been calling people right and left, and can you get your name, please? Corbin. Okay. Also. Okay. Got it. Let's see. Which class were you in? Were you in Cal 2? Last summer here. Okay, that's where it was. I was trying to pick when that was. Okay, last summer. Because I knew I'd seen your name before, and so I had another vice in a class last term, but it wasn't you. I can't remember his name now. It was either male or female. I don't know. Had 2 names very close to that. But okay, welcome back. All right, you've heard most of this before, so you haven't missed a lot. Did you get the word that we didn't meet last Wednesday?
Yes, sir.
Okay, did you show up?
Yes, sir.
Okay. Well, this is the first time we've met, so there's nothing new. This is not the current syllabus, but it's awfully close. I'm just giving changes to it. This number is my office number, but because either the voicemail is erratic, sometimes works and sometimes doesn't, and I get so far behind in it because I don't know when it's working and when it doesn't, and I have a backlog there. I don't know if you leave me a message there, if it records, I don't know when I'll hear it. So please don't leave me a message on voicemail. Call during my office hours. I'll explain what those are in a minute. If you don't get me, hang up, call back a little bit later during office hours. But don't leave me a message because I probably won't see it. Try emailing me or just wait and call again. So let me give you my office hours. Again, these are incorrect. These are from last spring. Here's what they are now. 8 to 8:30 all 4 days of the week, except Friday. Okay, 8 to 8:30, Monday through Thursday. On Monday, I have Cal 1 starting at 8:30 to 11:25, Cal 2 from 11:30, big 5-minute break, from 11:30 until 2:25, and then I have another big 5-minute break before this one starts, 2:30 until 5:25. So at 5:30, I eat my lunch. Okay, so that's how busy Monday and Wednesday are. So basically 8 to 8:30 and 5:30 to 6. Okay, that's all the office hours I've got on Monday and Wednesday. But the good news is, right after class, I've got office hours. So if you need to see me, right after class, or that 5 minutes in between class, if I'm going to run down to my office and try to eat a granola bar or something so I don't starve to death, as if I'm about to starve to death. But anyway, Tuesday and Thursday, much more office hours there. I have an 8:30 class, differential equations, that goes from 8:30 to 10:45. It's just a 3-hour course, so it doesn't go as long as the calculus does. So at 10:45 until 4:30, I'm in the office. 4:30, I leave to go to the Birmingham East Campus, and there I have a physics class that goes 5 to 6:30. So I'm out of the office then after 4:30. Okay, that's when Tuesday and Thursday. 8 to 8:30, 10:45 to 4:30. Biggest chunk of office hours right there. Then on Fridays, 2 Fridays this summer that I'll be there. This coming Friday and the first Friday in August, 8 to 12 on the Birmingham West Campus in B122. Okay. Now, the course description. This is not something I came up with or anyone here at the college. It was developed by a committee called our Articulation Committee between the 2-year college system and the state-supported 4-year colleges and universities in the state of Alabama, probably where most of you are coming from. Okay? And they decided if we teach this, they give you credit for it. So we'll try to get this. This is the third of 3 courses in the basic calculus sequence. The topics include vector functions. So let's pause there for just a moment, and I'll be using this book. And let me say this about the book. Are any of you Lawson students? I don't think you are you? Aren't you all transients? Okay. So my guess is none of you probably use this book at your home campus, do you? Okay? Were we using this last summer? I think we were. Huh? Yeah. I believe we probably were, but you probably don't have it. So I'm guessing not. Okay. If you have a calculus text from your home campus, use it. I've taught from several different calculus texts, and the table of contents are almost identical. I mean, the chapter numbers may be a little different or a little bit of change of order, but the topics are just about always the same. Okay? They may split, this book may put these 2 into 1, or this one may split these 2 into 2 chapters, or something like that, but they're almost always the same. So if you find the material in your book, if you have a book, do those exercises. Follow it there. It's not going to be far off from what I'm going to be presenting here. The calculus doesn't change. Okay? So topics include vector functions. In this text, that is vector functions, vector value function, chapter 12. Okay? Functions of 2 or more variables. Okay? Functions of several variables, chapter 13. okay, including, oh wait, I'm sorry, partial derivatives, that's also in chapter 13. That begins in 13.3, okay? Including applications, they're also in 13.3. Quadratic surfaces, now that we jump back up to 11.6. So that's probably where we'll be starting this class, 11.6, okay? Surfaces in space, quadratic surfaces. Multiple integration, that's chapter 14, exactly the same title. And vector calculus, that's chapter 15, okay? In this book, they call it vector analysis. And it says here, including Green's theorem, which is 15.4, curl and divergence, that's 15.7, surface integrals, that's 15.6, and Stokes' theorem, that's 15.8. Now, if we get that far, it'll be the first time I've gotten that far. We're going to get pretty close to that, but we may not get it all done. But anything that we left undone will have the groundwork that you can probably put it together from there. Prerequisite is Cal 2, which is Math 126 here, no co-requisite. Okay? Now let's see if I can get the textbook to come up. Okay. Now, I do not like about half of what's in here. I'll explain that in just a second, what I mean by that. All right. This text is Calculus by Ron Larson and Bruce Edwards. It's the 11th edition. Its publisher is Cengage Learning. I really don't care for Cengage Learning. However, Ron Larson is one of the best math authors that I've run across. So that's why I use this book, okay? Or we use it here. It wasn't just me, but others. Okay? It's a 2018, which probably means it's going to be good for another year or so. However, we all won't be coming back for calculus, hopefully. We'll pass it this time, right? But starting in the fall, we're going to go with the same author, but we're going to go with calculus with early transcendentals. Same book, same author, same material pretty much, but just arranged a little differently, okay? That's no importance to you, but if you do notice that will change. Graphing calculator, good idea, especially in those later chapters, okay? Paper, we'll be doing stuff in class, so unless you're really good about doing things in your head, good idea to have paper. Graph paper, we're not going to need that much, but if we do need it for a test or something, I'll try to supply it, but if you have your own you prefer, go for it. Pencils, now if you prefer ink, that's up to you. I'll make a confession here. When I do calculus, I tend to make errors, and you'll see me make plenty, so I usually use pencil so I can erase and not blot out with the ugliness in the pen, but you can do whatever you want. Now, as I said, this was Cengage is the publisher. They, just this college year, came up with this new subscription thing called Cengage Unlimited. And what that means is if you are taking one course or multiple courses using a Cengage text, okay, then for one fixed fee, $119, it's really $120, $119.99. But for that, you can have access to every Cengage book for the courses that you're taking. Okay, now that's in ebook format. Okay, if you want a paper copy, it's not on here, I don't think, but for an additional $8, you can get a loose leaf, no hardbound cover. You have to have a binder or something to hold them together, copy of it. So if you're interested in that, you can do it. Especially, I know Ricky's doing physics too, right? Then she can, physics is also, again, Cengage book. So the same $120, she gets both the calculus book and the physics book, if she chooses to go that way. Okay? Doesn't cost any more. If you're taking other courses that have the use Cengage, same price. You don't pay any more every book you use that time. Okay? So, anyway, in a sense, that's a pretty good deal. Okay? Just by every sense it is. I still don't like Cengage that much. Now, here's the caveat with it. I have to have some web assignments out there. Even though I don't grade them, I don't do anything with them, I have to have it. That way you have access to the ebook. Now, they give you a grace period at the first of the term, so if you go that route, even though I don't have it set up yet, you can still have it. But in a while, I'll try to have that set up because I didn't know I was getting the course. So it'll take me a bit, especially with all the other things happening. So I'm not going to go through all the advertisement here. It really irks me they have us put all this in the syllabus. But they do, and we have to do it. So I'm just going to scroll through this. I'm not going to go over it all, but somewhere here, oh, and by the way, yeah, there it is. You print a print rental for $8. So you don't get to keep it. You have to return it back at the end of the term. Even if you're taking it the next term, you have to go through it again. So for $8 more, you get that. Okay. Now, here are the other courses here at Lawson that are using Cengage books. So you see there's a bunch of them, but you're probably only taking 1 or 2 courses since you're just transient students. Okay. If you wanted to do multiple terms, which I doubt since you're a transient student, 2 terms would be $179 for 2 terms, or $239 for 2 years. Since y'all are not Lawson students, I doubt if that's going to be important. But if you do go through this, when you get your receipt, when you pay at the bookstore, get the receipt, hang on to it because that has your pen on it. That's going to be necessary for you to access the ebook. And then I'll also have to give you the web assign code, which I'm not going to use, but I have to give it to you because you need that as well. Okay, so the rest of that is just advertisements for Cengage. Okay, Blackboard. Okay, are y'all all familiar with Blackboard? Do you use it at your home campuses, or is it new to you? New? Did I hear a new? Or yeah, it is new to you. Okay, all right. Do you know how to get into it? Oh, you do. Okay, good. Yeah. If any of you are not familiar with it, you go to the Lawson State webpage. Near the top of the page, there's a series of blue tabs. The second one, I think, is Student Portal. Click on that, and then you'll come up the options, and one of those options, there's your student email, the Blackboard, and other things like this, student suite, various things like that. Click on Blackboard, and you'll get to it. The login, you use your last name, no, your first initial, last name, and the last 4 digits of your Lawson State student ID number. Okay? That's your login. Your password is your birth date. 2-digit year, 2-digit month, 2-digit day. Okay? So that's how you get on. And then I don't like this paragraph here, but it says, all students must use Blackboard to gain access to vital course information such as the syllabus. It's not there yet, but it will be. Handouts, there will be at least one on there. PowerPoint shows, I'll explain where those are. Activities, I don't put there, but the school may put a few. Assignments, I will put at least one there, but others in certain places, I'll tell you that in a minute. Announcements, that's usually coming from the college. And then it says, failure to use Blackboard will severely damage your ability to pass the course. I think that's a way overstatement for this course anyway. If I were writing this, I'd say the proper use of Blackboard could greatly enhance your ability to do well in the course. It's much more positive, and I think closer to reality. And it says students should always check the Blackboard announcements and task pages prior to coming to class. Why would they put that in there? What's sort of the understood rest of that sentence? In case I cancel class, right? Why else would you need to check that before you come to class? Well, guess what, team? Did I cancel any last summer? You remember? Don't think so. I usually do not cancel classes, especially late in the day like this. If I am physically able to be here, I'm going to be here. I may be coughing, sneezing, or whatever, but I'm going to be here every day that I can. Now, I know I've got 2 doctor's events, one appointment and one cataract removal coming up. That's on Tuesday or Thursday, so it won't affect this class any. So, I really don't care, but they require us to put that in. Let me explain how to find things in Blackboard, since all of you are fairly new to it, but some of you have been in a couple classes before. When you find and get to Blackboard, okay, and then when you get to your Blackboard page, you'll see over here your courses. Is this the only course, or some of you have two? Any of you have more than two? Okay. Then, when you see the course, you click on the course, the Math 227, and then you'll see the home page for this course. Now, over on the right-hand side is a series, and then on the instructor side, these are blue tabs. I don't know what color they are on the student side. I think they may be blue, but I don't know. They're split up into groups, maybe 6, 7, 8 per group, something like that. And the first grouping, something like the third one or so, says syllabus and book information. Okay? If you click on that, nothing's there right now, but as soon as I get this corrected, I'll put the syllabus out there when I get the office hours and those kind of things correct. Okay? That would be under that. Then the one next right below that says instructor information or something like that. And that's where I'll put my locator card. I'm going to show that to you a little bit later. It's not there yet because I just found out last night the room number for the class I taught last night. Okay? We had met on the previous Thursday, but they weren't sure if we were going to be permanently in that room or not. Last night I found out we were. So I just found out that last night, so I don't have that in this, because, like I said, I just corrected it last night and haven't had a chance to put it on. Okay? So that's under that. Skip down to the next group of tabs, and about the middle one there says handouts, PPTs, that's PowerPoints, and more. Okay? So under that one, I'll have your research paper instructions. Now I'm going to go over that here today, but then I'll have the printed copy, just what I go over now, I'll have out there. It's not there yet, but it will be there. Next after that, or sometime after that, will be all the possible PowerPoints we will have this term. Okay? Starting with, and we'll talk about where we're going to start, but I think I said 11.6 or something like that. I know we'll be concluding that. Yeah, 11.6 is the quadratic surfaces. Okay? And then all the rest of them. And there's a different PowerPoint for every section that we cover. Okay? So there's a whole bunch of those. And then somewhere after you see all those, I will put the link to the YouTube videos. Like I'm recording this now, it'll be uploaded sometime tomorrow probably, and then out there on in the playlist whenever I get the playlist set up, and hopefully it'll be fairly soon. Okay. Additionally to those, over the years, I found a few websites, or students have referred me to websites that they found useful or I thought might be useful in the course. So I put those websites out there too. So if you want to click on those and go to any of those, if you find them useful, you can use them. All right, so that's what's on Blackboard, and that's how you find it. Oh, let me tell you this about the YouTube videos. If you go to that right now, you can't because I don't have the link there, but if you were to, you see it's got tons of videos in it. Okay? What I do, like today will be the first one for this class, and when I get that and upload it, then I'll take off the one that's equivalent that I did last spring. And then when I go to the next, we get the next one done, then I'll take off that. So I'll be taking off the ones at the top and putting on the new ones at the bottom. You might say, why don't you just clear them all out and just put them on? Well, it has happened more than once. Not often, but it does happen. Something doesn't work. Either my computer dies, okay, I can't record, or the Screencast-O-Matic contract expires and they forget to pay the bill or something, or there gets to be a glitch in it, or even the supercomputer up in Huntsville messes up and we don't have a link, or our server messes up. There's just lots of ways that I may wind up not being able to record a class. So if I've left all those ones out there, then that gets covered. Even though I can't record this class, the recording from the previous time I taught it will still be there. Now, I won't start at the right place or end at the right place, but you can get most of the material from that. So that's why I leave them there, because hard knocks, I found out I need to have backup. So those are my backups. Okay, too much of that. Now let's deal with professional competencies, objectives, that kind of stuff. These are things they require we put in here. And, okay, I'll just leave it like this. The course student learning outcomes. Students will graph and classify quadratic surfaces, 11.6. Students will work with and perform calculus operations on vector functions, compute arc lengths, speed and curvature, describe motion in 3-space. Chapter 12. Students will work with functions of several variables, compute limits, take partial derivatives, applying them to tangent planes, gradients, directional derivatives, and the chain rule. Chapter 13. Students will form multiple integration techniques and apply them. Chapter 14. The students will perform line and surface integrals, applying them to Green's theorem, Stokes' theorem, and divergence theorem. Chapter 15. Okay, just like we saw in the course description, this is how we're going to approach it to go along with the book. And you'll also research and write on some topic or computer application in calculus. Now, before you get panicky or disgusted at that, it's a really simple paper. It doesn't even have to be as long as a 5-paragraph essay. Okay, we'll talk about the length a little later. It's just a simple thing, but it's to get you out of the book and into something that's a little closer to the real world. Okay? So, as I said, this one is 11.6. This is 12. This is 13. This is 14. And at this point, it starts cutting off at the top. Number 5 is 15. Okay? No. Number 4 is 15. No. Number 5 is 15. Okay. And then the writing competencies will be your research paper. So that's what we're gunning for. This is how I'll measure it. And you'll notice at the end of each section, now, except this one, because this is only one section, the 11.6 and chapter 12 will be on one test. Okay? And then the other chapters will be individual tests at the end of the test. Now, let's talk about this now while we're here. Do you prefer in-class test or take-home test? Take-home? Ah, what a surprise. I never saw that coming. No, I prefer it too. Because the way I test and the type of questions I ask, usually there's multiple parts, and to do it in one sitting in, say, an hour or something like that, that would just be huge time pressure and all kinds of pressure. And that's not what I'm wanting to measure. I'm wanting to measure how well you can solve problems. Okay? Okay, so I prefer the take-home. Now, let me also say this. Some of the other instructors don't like the idea that I use take-home tests. So, after some kind of gentle, guarded statements to that effect, I got the impression, and I think probably what I ought to do with it is I do require you to write out, when I say all the steps so I can follow how you got from here to there. If you just write down an answer, and that's all I see is an answer, even if it's a correct answer, you're not going to get more than 50% of that problem. Okay? I have to see your process. Okay? Well enough for me to follow that, yeah, you know you went from here to here to here, that I can see how you got from this step to that step to that step. And I skip a lot of steps myself, and you're going to see that. As long as I can follow, then I'm happy with it. But I just don't want just the answer. Okay? That was a lot of their gripes, was that there's applications out there that people can go and get the application to work the problems for them if you give take-home. Well, I don't know about that, but if that's all you write down as an answer, you're only going to get 50% of your credit. So give me all your steps. Okay. The research paper is the writing competency. Your last, and I'll get to that in a minute. So let's go on to here. How will I evaluate you then? Well, And they have this first sentence in here, and it's almost redundant. But anyway, research paper is required. That's not optional. That's not maybe required. It is required for the course. It will count as a test grade that cannot be dropped. Okay? Now, a chapter test will be given after each chapter or unit. That 11.6 will go in with chapter 12. And the lowest chapter test grade may be dropped. Now, why do I put may rather than will? Well, what if you didn't turn in the research paper? That's going to be a 0. You're going to need every test score you can to bring that up. Or you really did a lousy job on the research paper, then you're going to need every score you can to bring that up. Okay? Don't do either of those. Okay? The final test cannot be dropped either. Okay? Because the final test is going to be basically, it's not going to be comprehensive, but it's going to be using material that we've used in everything else before. So that's my best measure of your overall competency in the course. So that can't be dropped. So don't come at the end of the term and say, I've made all A's on all my tests. Can I exempt the final? No. Okay, the final cannot be. And the final is just going to be the last chapter test, by the way. And it only counts as a regular test score, but it can't be dropped. So the assessment will be a 100-point scale, so everything's graded on that. Then I average your research paper, all but one drop test score, and your last test, average them together. And if you're in the 90s, you're A's, 80s, B's, 70s, C's. Don't go down here, okay? Number one, since you're all transient students, I don't think any of your schools will accept the D transferred back. So that's not going to do you any good. I know they won't take an F, okay? And these would hurt your loss in grade point average anyway. May not bother your school. I don't know how they work that, but try to stay up here, okay? If it looks like, if something comes up and you see that you can't possibly get any better than a D or an F, it's way better to withdraw than it is to get a D or an F. The D and F is not going to help you at all. Withdrawal won't help you, but it won't hurt you. These would hurt you. Okay? Now, whoever came up with this syllabus had a ridiculous, in my mind, a ridiculous statement here. And I changed it. Here's how it used to read. The instructor always rounds up, never down. That's what the first statement was here. And then this statement was in there exactly verbatim. For example, a 79.5% will be rounded up to an 80%, which is a B. But a 79.4% would remain a C. Well, guess what? That's normal rounding. That's not rounding up, never rounding down. That's rounding down. So I just took out the first sentence and said the instructor rounds grade more. 0.5 or higher is rounds up, and a 0.4 below rounds down. Okay. Just do that. Absence. Try to be here every day. I'm going to try to be here every day. You do too. But if you can't make it, I'm recording everything I can, and hopefully you can follow. Okay? But try to be here. You can't ask a recording a question. Okay? You can't interact with the recording. You can just sit and listen to it, and that's pretty boring, I would think. Okay? So try to be here every day. And like I said, I've already hit withdrawals, so I won't go over that again. Makeup work really sort of doesn't make any sense. You have a research paper that you can turn in any time during the term. The take-home test, if you aren't here the day I pass it out, pick it up the next day you're here and try to get it in. Now let me say this about your testing though. I always give you at least a week to turn in a test, okay? And there's two reasons for that. First reason is there's always one more class day in between that you can ask me questions. For instance, if you can't understand what I'm really gunning for, yeah, I'll try to explain or amplify or whatever. Now, here's a question I will answer, but probably not to your satisfaction. Can you do number 7? My answer will be yes. And that's all. If you ask, will you do number 7? My answer will be no, okay? Because that's a test question. However, I will do any problem you can find in the text. So what I suggest, if you have trouble understanding what I'm asking for, find a problem like it in the text, and I will work that one, and that hopefully will give you enough guidance to go on and answer the question on the test. Understood? Okay. So that's the first reason. You always have one day to ask questions. Second reason, you always have a weekend to work on it. In case you work somewhere and you have limited time during the week, maybe the weekend is the only time you can catch up. Maybe some of you work weekends too. I can't help there, but but anyway, that's why I give you a week. Okay, lateness policy, I try to start right on time, but you see I don't always. And really, I probably won't always, because I have 5 minutes between the last class and this class, and during that time I usually have to run down to my office and maybe eat a granola bar or something, because I have 2 5-minute periods between 8:30 and 5:30 in the day. Only 2 breaks of 5 minutes each, okay? No time for lunch, so my lunch comes at 5:30, so I usually need to eat a little something in between. But I will try to make that as short as possible, okay? Now, this academic integrity, they put this in, I guess it's required. Let me summarize it for you. Plagiarism, don't do it, okay? Read this if you want to. Read all this. Cheating, don't do it, okay? Just don't do it. It's not doing you any good. If you need this material for your upper level courses, which I'm guessing you do because they require it, then for you to plagiarize or cheat, it's not doing you any good, okay? Do your own work, okay? Now, because they're take-home tests, does that mean you can't work together? No, I don't necessarily recommend that you do, but if you do work together, make sure everyone is contributing, because again, if you're just bleeding on somebody else, off of somebody else, that's not doing you any good, okay? So I'll leave it like that. Then professional decorum. My goodness, I don't know what these administrators, they just don't have enough to do. I really don't care too much here. I'll just put a few things. If you sleep, please don't snore, because then you're bothering the other students, okay? So if you can sleep quietly, I don't care. I mean, I'd rather you be awake, but it's not something I'm going to kick you out of class or something like that, okay? Eating or drinking. My wife can tell you sometimes she needs caffeine if I'm talking, so you probably do too, so I have no objection. I will say this, if you make a mess, you clean up the mess, okay? Understood? So I don't care about this, except in the fact of, if you're bothering somebody else, don't do it, okay? Don't do it. That includes speaking out of turn, rudely, stuff like that. That's not going to happen, I don't think. Okay. Wearing inappropriate, oh, you got a cap on, you got to do that. No, I don't care. If you're, I actually had, I didn't have him, but I knew a professor at University of Georgia when I was doing my master's. He was convinced that, oh goodness, what do you call those? The lights in the tubes. Well, those lights. He was convinced some sort of radiation was coming out of that, and he always wore a hat when he was in rooms lighted by that. And I wasn't about to tell him he couldn't do it, nor was anybody else. So, you know, if you have reasons that you need to wear headgear, I don't care. Unless it's a big hat that's blocking someone else's view, then don't do it. Okay. All right. So I won't go there. If you're wearing clothing that's distracting to other students, don't do it. I mean, wear clothing, but don't wear that kind of thing. Okay, course concerns. If you feel like I'm not giving you a fair shake, then first come see me. We'll try to work it out. I'll try to adjust. If there's something I'm doing or not doing that you find distracting or unhelpful, let me know. Next, if you don't get satisfaction with me, see the department chair. Oh, that's me, okay? So you can see me again, and we'll try to work it out again. Or we'll go to the associate dean. He's my boss. The full dean, she's his boss. Vice president, they're everybody's boss, or the president. We'll go as far as it takes. We'll try to work it out, okay? The website, I guess, is listed there because it has the procedures to go through all that. All right, the next one, statement on discrimination and harassment. Boy, let me summarize that. The college doesn't condone it, tolerate it, want it to happen. If it is happening, please let us know. We want to nip it in the proverbial bud and not have it happen. Now, I've been teaching here several years, more than 20 years. I don't remember exactly how many. And so far I have seen basically nothing, I think, that would classify as discrimination or harassment. Now, I like to throw in one more, bullying. Okay? Since most people are not going to do this in front of me, so if it is happening, I haven't seen it. If you sense or think it is, or even suspect it is, please let us know. We want to deal with it. We'll deal with it fairly, due process, all like that, but we don't want it happening on this campus, or on either of our campuses, or any of our campuses. So, do that. So I'll just end that like that. Okay, Americans with Disability. If you haven't noticed already, I'm hard of hearing. Okay, so I'm a little sensitive to this, so please let us know. And you don't need to tell me anything. We have professional, Dr. Renee Herndon on this campus, Ms. Janine McCoy-Jones on the Birmingham campus. They know exactly what to get, exactly what to ask for, exactly what to do with it, and then they'll get the word back to us what we need to do to accommodate. Please let us know. We want to give you the fullest opportunity to get the maximum out of the classes you take here. Okay? Here was the course calendar for last spring. I'll update this when I get your syllabus updated. It's just right off the website. You can go to the website and see it. It's under academic calendar. I'll eliminate a few things on it, but this is the bulk. And then when you've read and understood, I get it updated and everything, here's the acknowledgement form. You can either type your name on this and email it to me, or you can print off a copy, sign it, and give it to me. Either one. Once I get it out there. It's not there now, but as soon as it is. Any questions so far on the syllabus? Any at all? Okay. That probably took too long, sorry. Let's move on to the research paper. And again, this is not meant to be a big onerous thing, but I do want you out of the book and into a little bit more of a real world situation. You get to choose your topic. Any topic you want to write on. It can be, as long as it relates to the course, calculus in some way. It can be a person. There's tons of people who have contributed a big deal to calculus. As we saw in here, there was Stokes' theorem, okay? Green's theorem. Who was Stokes? Who was Green? You could write on those people, and there's plenty more. There's two that I have already called their names. You can write about the theorem that they came up with, or anybody, like divergence theorem. That wasn't someone's name. That's a theory. How do we use that? Where do you use it? Do they use it in your field of study? Okay? If so, that might be a good application. A phenomenon. Okay? That can be just about anything that uses calculus to explain or describe what's going on. I love the application papers. Okay? I'm guessing most of you are pre-engineers. Is that right? Okay? How do you use this calculus in your field of study? Or how do you use it to explain something that's maybe not in your field of study, but something you're interested in? Anything such as that. I'll give you a real quick example. A guy sat in that back seat right behind you. He actually lived in McCullough, but he was going to Jeff State. But I guess he and the Jeff State math teachers didn't get along or something. He just decided to try doing math here. And he was in my trig class. And he was a pre-forestry major at Jeff State. And he wrote his paper on the use of trigonometry in the forestry profession. You think that was much of a paper? It certainly was. Because guess what? As a forester, one of the things you might wind up doing is going out to a field of trees, and you're going to be making an estimate on the purchase of that lumber, and you need to be able to estimate how many board feet of lumber there. So what they do, they take the height of the tree, and they take the approximate diameter midway up, and they calculate board feet. So how do they get the height of the tree? Do they put a tape measure tied to the bottom and climb the tree and measure how high it is? You better believe they don't do that. What they do, they use the sextant. Stand so far, measure the distance from the tree, use the sextant to go up to the highest marketable piece of part of that tree, and they get an angle, and then by the distance and the angle, they can calculate using tangent. So he wrote his paper on the use of trigonometry, which is a major use of trigonometry in the forestry profession. It wasn't a great paper, but it was a good paper because it was something that was interesting to him. I love seeing those kind. Okay? So that's certainly a possibility. or any other subtopic about which you have an interest and relates to this. Some people may be amateur astronomers and use calculus in astronomy. That's in fact how Newton developed it, because he was trying to help goodness gracious, I always go blank on the guy's name. Kepler. Kepler tell why his laws of planetary motion work. He figured them out, what they call not experimentally, but the other word, empirically. He figured it out empirically, but he didn't know why they worked. And Newton developed calculus so he could explain to Kepler why they worked. So, I mean, this is a long roundabout thing. So anyway, anything that you have in interest. Now, here's something I've added, not really recently, but fairly recently. Any internet application. Remember I said some students have given me applications or told me about them they found useful? If you find something useful, say that you find on the internet a YouTube video or something that explains something that the book is blah, 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 and when I try to explain it, it sounds like blah, 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 you know, and it doesn't get any clearer at all, but you find that website, YouTube video or something, oh man, that's what they're talking about. If you can find something like that and want to write on that, that's perfectly fine too. And you can easily get a paper out of it. What was confusing about the way the book or I presented it, how you looked at other sources and found nothing that was helpful there, but then when you found this source, how it explained things that made it make sense to you, boy, right there you have a page or two of paper, right there. Okay, so what I would ask you to do is sometime today or next week, write on a piece of paper your name and the topic that you have selected for your paper. Now, you're welcome to change this later if you find out this topic is too narrow, too broad, or you really aren't interested in it at all, but at least get started thinking about it, okay? Now, the other thing that does, the first one that turns it in, if you turn in Isaac Newton, then the next person, nope, you can't do Isaac Newton, you've already got that one, but you could do his 3 laws of motion or planetary, or you could do something else related to Newton, okay? So, do that. Now, since that's going to be wasting a whole piece of paper with just your name and the topic, here's something else you can put on that piece of paper. Has nothing to do with the research paper, but is something that sometimes comes in handy. Periodically, I'll get an emergency phone call or someone will come and bang on the door during class and say, thus and so is in your Cal 3 class. I need to get in touch with them right away. This is going to be not a student, but an administrator or someone here at the college. Do you have a current number? The number in the system is not working. So if you've given me your very best phone number, then if you want to give it to me, you can. If you don't have to. Okay? Now, if that very best phone number happens to be a cell phone, my guess is going to be, that'll be fine. Unless there's a possibility that that cell phone could die, the battery go bad, it gets run over by a truck, you leave it in the car, something like that happens. If you want to give me a good backup number, that's fine too, like Mama's landline or something like that. If you want to do that, you can. You don't have to if you don't want to. Or, it's the only other scenario I can think of, if you happen to work and they don't let you have your cell phone or talk on your cell phone at work, but that may be the time when someone's trying to get in touch with you, and they will let you have, especially emergency phone calls coming in, then if you want to give me your work number, you can do that. So you can give me no numbers, 1, 2, I can't think of any reason I need more than 3 numbers. I don't need any, but you know, if you want to give me up to that many, that'll be fine. Okay, so you can write those on a piece of paper too. Now, you will need to find at least 1, but 2 or more are better, outside sources for your paper. Like this book here, let me just open to it somewhere here, and maybe there's something in here on Dirichlet. It ran into that this morning, okay? Somebody who came up with a function, okay? Well, this book can't be your source. It can be the source of ideas for your paper, but you have to get your sources for the paper outside the book. That's the whole point. Get you out of the book, more into the real world, at least sort of. It can be, your sources can be any book, journals, articles, newspaper, magazine, whatever materials that you can find in the library. And here's where you get a little shaky, or any legitimate source. Now that's the key word, legitimate source found on the internet. The internet has to be probably the most incredible thing that's ever been developed during my lifetime. In 1951, it wasn't in existence, and it is now absolutely amazing what you can find on the internet. Two problems, maybe more than two, but at least two I'm thinking of now. One, at least half, and probably way more than half of what's on it is total garbage, okay? Number two, sometimes it's hard to figure out which half it is. So be very wary of the internet. If you have any doubt of its validity, run it by me. If I've seen it before, it's, oh yeah, that's perfectly fine, yeah, that's well established in the literature, you can use that. Or, never heard of that before, and I've never heard of this guy before, and this sounds really bogus. Check and see, verify this somewhere else. If you can find other sources that support this, that are not tied to this, yeah, it'll be okay. So run it by me if you're all in question. The textbook is not an outside source. It can be a great source of ideas, but it can't be the source for your papers. Okay, paper needs to be at least one word process page of text. Notice that eliminates handwriting or typing. Word process page of text. Now, what do I mean by that? Well, if you choose to use a format, do whatever you want to, that has some sort of header at the top, and then skips a few lines, and then you have a title, and then you triple space, and you start typing right here. One page of text is going to go to the bottom of this page, and then on a second piece of paper, come down from the top until it reaches that far. That's a page of text, not something that you squeeze into one piece of paper. No, it's going to have to be at least two pieces of paper for one page of text, okay? Now, I want it double spaced. This is single space. I don't want that. I want it double spaced. There's not that much writing to do, okay? I want 12-point or 12-pitch font. I don't want the little bitty 9 that I can't read, that, especially with a cataract, it drives me nuts. Nor do I want 26 points that's going to fill up the whole page with 3 or 4 words. That's not going to work either. Do standard. I don't care what font you use as long as it's easily readable. Okay, I don't read Old English or hieroglyphics or something silly like that. So keep it something, and there's tons of really readable fonts out there. Most word processing packages default to Times New Roman. This is in Arial, Courier. I don't care what you use. There's lots of really good, easy to read fonts. Use whichever you want. Try to keep your paper less than 2 pages, just because I don't want it to be an onerous thing for you. Now, if you get so excited about your topic it goes over to 3 or 4 pages, I don't care. If you're that excited about it, I'm happy, as long as you're doing a good job. I've been teaching here almost in this room since, boy, I can't even remember what year I started. 89 or something like that. May have been a long time. No, that would be 30 years. That would be later than that. 96 maybe, I don't remember. Yeah, I started working in Southern Research at 89. But anyway, well over 20 years. Now the first 2 or 3 years I didn't require papers. But everything since then, so well more than 15 years, I know I've required papers from just about every class I teach. I've taught either 4 when we're on quarter system or 3 terms every year, summers included. And usually I have, like this term, I have 5 courses. Some terms I've had up to 8 or 9 courses. Most courses are more than this. On average, it would be about 15 students per term. So I've seen a lot of papers. And only a couple of times this has happened that someone, and the best I can figure out, they figured out, well, I can't write a good paper, so I'm going to write a long paper. I don't want that, okay? I'd rather have a nice, short, well-done paper than a real long one. And here's why. When you turn in the paper, it's a 100-point paper, okay? As I start reading it and find errors, I can hear you now say, don't read it! Yeah, I want 100 points. No, I'm going to read it. If I start finding errors, I start taking off points. So if you write a really sloppy paper, but make it really long, substituting quantity for quality, then the more I read and the more things I found to mark up, you're losing more and more points. And if you drag it on for page after page after page, you're losing more and more points. So don't do that. That's going to hurt you. If you write a good paper, whether it's 2 pages or it's 3, 4, 5 pages, if it's a good paper, you're not going to lose that many points anyway. And I'll enjoy reading it. If you're fired up about it, I will have a good time reading it. So I just say shoot for 1 to 2 pages. Okay? If you go over it, no problem. If you go less than a page of text, you're going to lose points. Over, no direct points lost. Okay? You may use any standard format you'd like. Most English classes teach MLA, Modern Language Association. Fine with me, I don't care. A lot of science organizations use APA, that's American Psychological Association. They came out with this format early on, and everybody said, wow, I can't improve on that. That's a really good format. So lots of subject areas use APA. I've been a member of several professional organizations. Seems like every one of them has their own little format. I don't care which one you use. The important thing is be consistent, okay? If you start blocking paragraphs, block all your paragraphs. If you start indenting the paragraphs, indent them all. And indent them at the same place. If you start 5 spaces in, and if this one's 10, and this one's 3, and this one's a block, that's not consistent, okay? So please be consistent, okay? Spelling, grammar, sentence structure, all that kind of stuff, if you make errors in it, you lose points, okay? But guess what? Every word processing package I think out there has spell check, and most of them have grammar check. Use them, okay? Now let's get to another issue. I'll get to that later, but remember that, okay? Also use good proofreading. I had a senior English teacher in high school. She used to use this analogy. She said, when you do something, a fairly major paper, she said, do it, get it done early, then set it aside, and she said, let it rest. I thought that was a strange way to say it. She said, then pick it up a few days later and read it, and here's what she said, with fresh eyes. And I thought, oh yeah, good description. I've done that before, and I've done it with emails too, by the way. When I'm typing in an email or paper or anything else, I know exactly what I mean it to say. And when I go back and look at it, it goes type, 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 read, type, 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 read. It's going to say exactly what I want it to say, whether it actually says it or not. If I let it rest and pick it up a few days later and read it with fresh eyes, I'll be reading along and say, what was I meaning here? And if you say that about your own paper, guess what? I'll be saying that about your paper. So use good proofreading, okay? Let it sit, pick it up. If you can't follow it later, the odds are I'm not going to be able to follow it. So make it say what you want. Like I said, when you read it immediately after typing, you're going to think it's saying exactly what you mean it to say, whether you've left out a word or not, okay? So anyway, check that. Content also matters. All these things matter, but content does. I mentioned Isaac Newton, I think. I've read so many papers on him, and I don't mind. You can turn it to Isaac Newton. But I actually remember one. I don't remember the year in question. I just will make up the year. 1694, but when they typed it in, it became 1964. I said, no, Newton was long dead about that. You know, they just got two numbers. So content also matters. I've also seen this. I'll use, well, no one in particular. When you first, if you're writing about a person, a lot of times people will put, after they mention his name, in parentheses, the year of his birth and the year of his death. I've had some papers like that. They'll put that, fine, I don't care. But then on page 2, they have them dying on a different year from page 1. That was not that long a paper, so it should have been the same year, okay? So content matters. Be consistent, okay? You'll lose points for that too. It's due the last day of class, not the last day of finals, but the last day that the class meets. But please don't put it off till then. That's why I'm asking you to give me a paper topic this week or next, so you can start thinking about it. And believe it or not, you'll never have more time to work on the paper than you do right now. Because later in the term, you're going to have more tests, you may have more projects, you may have labs, you may have other things in other classes. It's going to pile up at the end. Get it done now. So remember when I was saying how many papers I've read? I mean, it's been, I haven't set a number. It's an awful lot of them. And here's a generalization. This isn't always true, but generally, the best papers I get sometimes are the ones I get earliest in the term. People have more time to do it. And then it just is a gradual decline in general. And usually the worst papers they get, usually, not always, are those turned in at the end of the term where you turn them in, didn't even use spell check, grammar check, or anything else because you're in a rush to get it in before you start losing points. So please don't do that. Get started early, get it finished early, do a good paper. Okay? Now, I've had some real dogs at the beginning of the course. I have some great papers at the end. But the general rule is it's downhill. Okay? So get it done early. Give yourself your best shot. Now, if you turn it in after the last day of class, the last day we meet as a class, then you'll lose points. That's the stick. Here's the carrot. If you turn it in during the month of May, you'll get 2 bonus points added to whatever your score is. I'll just add 2 more points to it. Okay? You turn it in the month of June, 1. You turn it in July, you just get your score. So that's a little bit of a carrot trying to encourage you to get done early. Okay? Now here's one more thing that I require. I don't know of anyone else, but I just like to have this. When you submit your paper, please attach a single page from one of your sources. What if you had 2 or 3 sources? Pick one, any one source, I don't care. And then print me a page from that source. If it's something you got out of the library, take that over to the copier, copy me a single page from that source. I don't need the whole source, just a single page from it. Something you got off the internet, print me a single page from that source from the internet. I just like to have that. I want to have it. If you don't turn it in, you'll lose points. Okay? Any questions on the paper? Get started early. Get your topic. Start looking for sources. Try to get it. Now, the month of May, we have today and tomorrow and Friday. And that's all, folks. So if you get it to me today, tomorrow, not likely today, tomorrow, Friday, you get the 2 bonus points. June, 1 bonus point. You've got a whole month to do on that. But I actually received my first paper in this morning. My first class. We met last Wednesday. She turned in her paper today. She took advantage of the holiday weekend and got a paper done. Good for her. Any questions? We didn't meet last week. Sorry. Y'all lost that opportunity. All right. If no questions on research paper, then let's go to the locator card. Now this one I have updated. Every other class got the old version. You got the new version. Okay? This is summer 2019. My name's the same. My phone number, that's the office phone number here, is the same. Email address is the same. I'm in mathematics. And then let's just scroll down so you can see the whole day a little bit better. Okay. All right. Monday through Friday, on Fridays that we're here, I'm on campus, try to be on campus by 8 o'clock. Now, sometimes traffic will get in the way, sometimes other things might, but I try to be here by 8 o'clock. On Monday through Thursday, I have office hours that first 30 minutes every day because classes don't start until 8:30. Mondays, Cal 1, Cal 2, Cal 3, back to back to back with not even 15 minutes. 5 minutes between the classes. That's all. So my lunch is at 5:30 this evening. Okay. That's all I got. But I eat my lunch in my office so you can come see me right after class 2. I'll meet with you here and then I'll go eat lunch. It doesn't matter. Tuesday and Thursday, though, I've got a little bit more. Differential equations here. 10:45, also advising. Sometimes I'm up here a few more minutes, especially if students have questions or I have a few things to do on the computer. But usually I'll get down to the office. Lunch I eat around 12:30, but like I said, I eat in my office. I bring my lunch, so I'm down there. You can come in anytime there, pick up again. But then I leave at 4:30 to go to the Birmingham East Campus and teach my physics class over there, and that's in K214. I did not know that until today, or yesterday. Last night is when I found out what room I'd be teaching in. So that's why I hadn't posted this on the thing. I'll try to get it out there as soon as I can. And I'm there until 6:30. I'll leave after 6:30. And Monday, Wednesday are the same as Tuesday, Thursday. So those are the same. Now, For this coming Friday and the first Friday in August, I'll be on the Birmingham West Campus Academic Building, B122, from 8 until 12. And I usually don't really eat lunch. We're required to put it on here. I usually just bring a snack. I eat it sometime around 11 to 12, sometime in there. I'm almost always there well after 12, but we're required to be there 4 hours, so I have to do this 4 hours. But I'm usually there early and leave late. Quite often the same thing on these days, too. So any questions on my locator card? You have access to me right after class or Tuesday and Thursday, middle of the day. Plenty of office hours there. Fridays, for 2 Fridays, I'm on Birmingham campus. So any questions? All right. That will be posted under instructor information. It's not there yet, but it will be. All right. Now, I'm going to close this out and change here. While that's trying to come up, I don't know what's taking so long. Safety is another issue. Now, there's no PowerPoint on this or no slide, nothing to show, but we need to be able to think about safety before a crisis happens. There's 3 major areas that we need to think about safety. We're not going to be doing anything here that requires safety, but there could be things happening. Can you think of one of those 3 things that we might need to be aware of concerning safety? Second? Weather, exactly. Have you been noticing what's happening in Indiana and Ohio? They've had tornadoes like crazy for it seems like more than a week now. Just about every day someplace else is having a tornado. Fortunately, we've been missing them now. That doesn't mean we're going to miss them for a while. Still is severe weather season. Even if it's not a tornado, severe thunderstorms can have straight line winds that can cause a lot of damage. Okay? So, if we hear that weather siren go off, what do we do? What's the general rule? Anyone know? Go low, go interior. Okay? Don't get in your car and leave campus. The worst place you can be in severe weather is in a car on the road. Don't do that. Go low and go interior. So here's what we do for you. You don't want to be in this room. Why? That tree right out there, big branches in it. If there's a twister comes through, some of those are going to come right through that window. We don't want to be here. So here's what we do. Okay? We're right here in this corner office, corner classroom here. We go out, we hang a left, we go down the little half flight of stairs right there, and then at the bottom of those stairs, we take a left again, go down one more flight, all the way to the lowest floor. This is the lowest floor in the building, and there we come out into a hallway that's just like this one, very similar to this one. Okay, we're down on the first floor. Now, right in front of you, you'll see restrooms. They're interior, almost the lowest level. There, the walls are close together, and you have lots of corners. That's where the greatest strength of the building is, in a corner, close walls. Okay? So actually, the restrooms are not a bad place to be. Of course, if it was severe weather close by, the odds are we're going to lose power. The problem of being in the restroom for a couple of hours is, if you lose power, you're in the dark. Okay? And it may not be the most hospitable place to be for a couple of hours in the dark in a restroom. So if you don't want to be there, that's okay. There's actually a couple steps below the restroom, and right at the bottom of those steps is, on the right, is the academic dean's office. Now, she's hardly ever here on the Birmingham campus. She's usually on the Birmingham campus. But when she is here, if she's there, or the associate dean sometimes uses that office, but he's mostly on that campus as well. And during the summer, actually, the guy who runs our summer enrichment program for high school students, he uses that office anytime they're out here on this campus. So if he's there, any of them are there, that room is a pretty small space, walls are close together, and you're interior, no exterior at all. Now, the additional thing, this wall back here on the first floor, the wall back here is backed up by soil. It's not a standing wall that's exposed to the weather at all. Soil is behind it, so that is one strong wall. nothing's going to pretty much, knock on wood, make it come down. So that back wall is the best place to be. And a corner is even better, okay, on the back wall. The next room next to that is a classroom. Probably close to this side, probably not quite this shape. It's okay to be in, especially if you're near that back wall, a corner, even a corner near the hallway. There's strength there. Middle of the room, try to stay out of it, even though I don't think very much can happen on the interior room like that. Then you go through on the first floor, some glass doors in the hallway there, and you're in the library area. The first room to your right there is a computer lab, which is smaller than a classroom, so the walls are closer and the corners are closer, okay? Right next to that is what I call the research room, which is where the atlases are and those kinds of things. Again, that back wall, backed up against soil, very strong. The corners are very strong. Anywhere near a corner or wall is okay. Don't go any further in the library because then you're on the exterior. And glass is something that can fly in a moment. Now, the place I haven't mentioned, which may turn out being the place of your choice, that would be the hallway. Now, the disadvantage of the hallway is there's no corners, okay? So you lose that strength of corners, but the walls are relatively close together and you're interior. But here's the big advantage of the hallway. If the power does go out, the hallways has emergency lighting. So that's a good, safe place to be. You'll be in the light, you won't be in a dark room, so it's not a bad place to be. Don't go to an exterior room, go low and interior. Okay? Now, in addition to that, you go down, if you hear the siren goes off, you go down in an orderly manner. Don't rush, don't push, don't shove. We don't want to stampede, okay? Go in an orderly manner, but go down, quickly, but not speed, okay? So go down the stairs, take them easy, and I'm going to be the last one out of the room. Right now, I see one person with a bad leg. So you're probably going to be next to the last, okay? I'll go down behind you or with you, beside you, to make sure you get down the stairs safely. We don't have any elevators in this building at all, so if anyone else turns an ankle, breaks a leg or something like that, and you're in a wheelchair or something, I'll be helping you get down. We may even, in that case, move down to another room, but if you're just somewhat slowed down, then I'll be with the last person out. When I get there, I will be carrying my roll book, and we will call roll. If we can't find you, if you decide, oh, the dogs are in the house, I need to go get them out. No, you don't, okay? The worst place to be is on the road. The dog won't do any good if you get killed in a car accident. So be there. If you are not there, we cannot locate you. When I call the roll down there, I have to come back up and risk of my life and health to look for you in a dangerous area, okay? So don't decide to go off somewhere. Stay together. Once we call roll, then if you want to mingle with others, you can. But don't leave the building until you hear all's clear. We actually had math meetings one February. This was probably 5 years ago or so. And we were up in Athens, Alabama, Athens State University. And the keynote speaker had just begun, maybe gotten 5 minutes into his talk. He's really a very interesting sounding guy. It sounded like it was going to be a good meeting. All of a sudden, here came the weather sirens. We had to evacuate. We had to actually go next door because the next door had a basement. We went down to the basement. We sat in the halls because they had emergency lighting. The power did go off. And we sat around and chatted and stuff for about an hour or so. Finally, they came down and said, it looks like all's clear. Go back. Well, weather was still unstable. They dismissed the meeting, and we drove home. So we drove up to Athens, sat in the basement for an hour or so, heard 15 minutes of the talk, sat in the basement for an hour or so, and drove back home. That was the meetings that year. So things do happen like that, but you stay together, you stay close. Okay, so that's weather. One down, 2 to go. 2 other safety issues. Fire, exactly. That would also include something like a chemical spill or something like that. Something that happens inside the building, we need to get out. Let's take worst case scenario. Worst case scenario, my computer blows up, okay? And it starts arcing and sparking, sets my papers on fire, sets the desk on fire. What do we do? procedures in case of a fire that initiates in this room. What would you do? Anybody? What would be your first response? Okay, yeah, here, going out the door. Okay, we're all going to leave the building, get to safety. Who cares about the rest of the classes in here? They don't burn and smoke inhalation and that kind of stuff. Is that what you meant? No. We need to do something else. We are going to leave for sure. Oh, boy, fire alarm. Great idea. Actually, before that, there's one other thing to do. Say again? Yes. Okay. Actually, the better number than 911 is the campus police. Now, the door I come in has a piece of paper on it with highlighted what the local campus police number is on this campus and Birmingham campus. If you come in a door like that, take out your cell phone. See, I don't bring my cell phone to class, so I don't do this because I don't want it going off while I'm teaching. So it's down in my office right now. So put that cell phone on speed, that number on speed dial, so that you can get in touch with the police. That's not somebody's office number. That is a number for the duty person on watch at that time has that on his or her belt. Somebody will have that on their person 24/7, or as long as anybody's on campus. So that's the number, the best number to call. If you don't have that on speed dial, then 911 is next. Okay? Then I'd say one, preferably two people go to pull the closest alarm. Where is the closest fire alarm? Any ideas? Any ideas?
Hallway.
Second?
Hallway.
Hallway? Not any of these hallways, because this is the old part of the building, built before fire alarms were coded. We don't have one anywhere inside here. So where do we go to get it? Go out of the room here, hang a left, go down that half flight of stairs, but then go over here to this corridor and go through that corridor. That's a right through the corridor. As soon as you come out here, this is the new part of the building. The reason it doesn't show up here, this is second floor, that's first floor. Okay? When you come out there, you will see on either side, that's the new part, fire alarms to the left, fire alarms to the right. So there will be one in both places. I say two people go down and see if one trips or falls or something, the other can get there and pull the alarm. Okay, then okay. One other thing. The fire is blazing in here. You don't care if my room gets burnt to crisp, do you? What should we do? And I'll do it, but I need someone to get it for me. Fire extinguisher. Now, where's the closest fire extinguisher? Anyone know? Okay, you go out the door here, hang a left, and within 5 feet of where I'm standing, right there. Can't get much closer than that. There's the fire extinguisher. I know some of you guys, and maybe some of you gals too, have always sort of wanted to hear, wouldn't that be cool to break that glass and get it out of there? You can't do it, right? Then you can do it. So knock yourself out. Somebody go get the fire extinguisher. I will be doing what I can. I'll operate the fire extinguisher if necessary. Somebody dials 911. Somebody goes to pull the alarm. Someone gets me a fire extinguisher. Then we all get out of here. Now, where do we go? Okay. Again, we go out the door here, hang a left, go down the half flight of stairs, hang another left, go down this full flight. This time we go out, not in. Okay, we're trying to get out of the building. And we go out, they used to say 75 feet from the building. Now they say go all the way down to this parking lot. This is the room that we're in here. Here's the exit right there. Go down to the parking lot right through there. You'll see by Ethel Hall building. We'll meet down there as a group. Now here's what you don't do. You don't say, hey, the building's on fire. No more classes today. I'm out of here. No. We stay in a group. Same reasons as before. I'll be the last one out because I might have been fighting fire or whatever and helping whoever needs it to be out. We all get down there together and I call roll again. And guess what? If you're not there for roll, we have to assume that you're somewhere stuck in the building, so myself or somebody else, a fire professional, has to go in looking for you, risking his or her life and health. don't leave. Stay together until we get word, well, it looks like school's over for the day. It looks like anyone in A building is through for the day. Whatever. Now, also, if it did start in this room and all we hear is the alarm go off, then we just all proceed out. We don't have to do any of those other things. We proceed out of the building and down to the parking lot. And again, stay together. All right. Covered fire. 2 out of 3. External emergency, internal emergency. What's the third one? Unfortunately, we never even used to think about this. Nowadays, you have to. Active shooter. Okay? Now, as far as I know, there's only been one community college in the whole U.S. that there's been this incident. But there's been several universities and several movie theaters and outdoor concerts and other things. So you have to be thinking about it. Now, guess what? I'm hard of hearing. And that goes for the alarms and everything else. You will hear them better before I will. But you also, if there is a pop, pop, pop that could be gunfire, you'll probably notice it before I will. So let us know. What do we do in case of active shooter? What's the general procedure? Any ideas? Number 1, I want to lock this door. Fortunately, I have a key for the door, but there's no keyhole on the inside of the door. There's not even any button you can push on the outside on the edge of the door. I have to physically go out into the hall and then, with active shooter, get the right key and get it locked. And I don't want you pulling the door too when you get outside. Okay? Let me get back in, then we'll pull the door to. Okay? We turn off the lights. But while I'm doing that, what are one of you doing? Dialing either, preferably, campus police, or if not that, 911. Okay? Immediately. And as soon as that call gets made, everybody turns off their cell phone. Okay? We want this room to be perfectly quiet. We don't want any phones going off. Because if I have this off, we turn off the lights and we get out of sight. So if anyone looking in will assume nobody's home. Turn off projector, all that kind of stuff. The bad news is, though, it's passed right through there. I don't have a key for that door. Now the good news is, for this summer, they have been keeping these doors locked. I unlocked this one because I'm here, but y'all weren't in here. But Dr. Bryant, when he comes, he has to come in through here because that door is locked. He doesn't have a key for that. So what we'll do is make sure that door is closed. If it's locked, then we have another safety. Okay. If that door happens to be unlocked, and I'll go around there and check. If it's unlocked, then what we do, we could lock this door because it has buttons here. But that's not a good idea because it locks it from the inside, not from the outside. So that does us no good to lock this door. Don't. That locks us in. This door has a deadbolt. Great, but I don't have a key for that. But that door has buttons just like this, and it locks from the outside, not the inside. So that is the one we press. If that door to the hallway is unlocked, we have no way to lock that. So we can lock this. But we close this door because you can see through. And we'll invite that class to come join us because we don't want them to get shot either. We'll turn off all lights every door closed, that last one locked, this one all lights out, and then we'll all get back here. Why back here? You can't see us through here. He could shoot through the glass easily. He can shoot through a door of this grill pretty easily. Maybe not super easily. But he's going to have a hard time shooting through a concrete block wall. In fact, if he tries, most of that is going to come back to him because he'll have more stuff coming back to him than will make it through. So we're back here as quiet as we can be, not talking, not doing anything else. Now, if somehow he manages to get into that room and to break the glass in the door we locked, come through that next one and make it into here, you don't be the hero. Okay? Because you're the future. My life it's mostly back here behind me. I'm the task. Let me take care of anything that would happen. I've been in the military. I'm not very good at very many things, but I'll do whatever I can. You protect yourselves, okay? Don't be the hero, okay? Any questions? Active shooter. We wait until someone comes with authority and says the coast is clear, you can leave the building. Okay. Any questions? Okay, those are the safety issues. Goodness gracious. All right. Ready for calculus for a change? Let me eject this. Does anyone need a break? I know I've been going on and on and on, and it's late in the day, so if you do, we can take one anytime. Just let me know if you do need one. Now, before we get started here, I told you where the course is set up to begin. But what I want to hear from you, do all of you feel like you're ready to start at quadrant surfaces? The chapter that quadrant surfaces is in is chapter 11, which is vectors in the geometry of space. Do you feel like you're ready to start at the end of that chapter, or do you need to start somewhere before it? Just let me know. Quadrant surfaces okay, or do you feel like you need to start a little earlier than that? Anybody? Huh? Quadrant surfaces okay? Okay. Second? Okay, we'll talk about that, but do you feel like you're okay with vectors in geometry of space? That's the bigger question. You're okay with that? We can start after that. Is that right? Okay, if you think you need to start earlier, we can start earlier. You okay? All right. Well, to answer your question, that's where we'll begin, and I'll explain what these things are. And if find your text, if you have another text and don't want to buy this one, and you look for, actually the title of this section in here doesn't say quadrant surfaces, it says surfaces in space. But then they talk about various surfaces, but then get to quadrant surfaces. Okay, other books actually call that section that. It's right at the end of a chapter. That's why I asked if you need to start earlier in the chapter, we can do it. But if you feel okay, we'll start here. That's where it's designed to start. See, I have no Lawson students here. If there were Lawson students here, I'd say, where did you end your course last term, or whenever. So if you're okay, that's where we'll begin. So let me get this set up for that then. So I didn't have this loaded earlier because I didn't know where we'd be starting. Well, number two, it was on a different flash drive. Okay, 11:6. And I'll try to answer your question there as soon as I can get this to come up. And again, we're going to go for about an hour and a half, which means we have about an hour to go, right? A little over an hour 15 minutes. So if you do need a break, this would be a good break time. What you think? You do? So it is a good stopping point. So I'll get this set up to go from this slide. So let's keep it less than 5 minutes if at all possible. Just get back as soon as you can. I think I'll go on and do from current slide. Wait a minute. Okay. And we'll pop. Oh. We are now recording. You just can't see the projector, but we are recording. Chapter 11 was talking about vectors and the geometry of space. Now, we're not going to do all of 11. We're just going to start at 11.6, which is surfaces in space. Okay? Now, we'll talk about some other surfaces first before we get to quadrant surfaces, but just to get you an idea of what we're talking about, surfaces in space. We'll recognize and write equations for cylindrical surfaces, that's the first kind, Then we'll recognize and write equations of quadric surfaces. That's the part we're really focusing on. And then we'll recognize and write equations of surfaces of revolution, which many of those are quadric surfaces as well, but not all. Okay, so let's start with cylindrical surfaces. Okay, when you think of a cylinder, what do you think of? A can, okay, a tin can, use circular base, certain height. That is one type of cylinder. That's called a right circular cylinder. Right means it stands at 90 degrees to the surface. Circular means the area is a circle. A cylinder doesn't have to be circular. This is a cylinder, okay? Now it's a weird one because of that indentation. Your drink bottle is a cylinder, okay? But those aren't the only cylinders. Actually, this wall is a cylinder, okay? So that seems strange, but it is. And here, yeah, okay. It says we've already studied two special types of surfaces. Spheres, these are solid things, spheres, and planes. Now, a plane is a surface. This wall, of course, is a plane. A slanted surface, the tabletop is a plane. Anything that is two-dimensional, no matter where it's going, that's a plane. Now, let's go up to the spheres for a minute, even though we're not meant to stop there. But what is the basic unit that the sphere is drawn from? That's sort of a bad sentence, but what would that be? What two-dimensional figure do you relate with a sphere? A circle, okay? And this would be, let me get my pen set up. I don't draw circles very well, but let's just imagine that's a circle. Use your imagination, okay? So that's a circle. If we take that and rotate it about any axis, then we get what we, I don't draw spheres very well either. Okay, that would be a sphere, okay? Now, what does a circle, what is the equation of a circle? Does anyone know? Basic equation for a circle. X squared plus y squared is equal to r squared. Ring a bell? That's the basic equation for a circle, where r is the radius of the circle, the distance from the center to the edge. Okay? Now what do you notice? Squared term, squared term. What makes it a circle? Same coefficients. This could have a ax squared, but then it'd have to be plus ay squared equal to r squared. Okay? Same coefficients for the x's and y's. Now, this circle is centered at the origin because you have nothing following that. If it's any place other than the origin, it would be x minus a squared plus y minus b squared is equal to r squared. Okay, now the center of this circle would be the point somewhere out here, A, B. You know, A this way, B this way. That point right there. That would be the center of the circle here, rather than the origin. Okay? This would have the center at the origin. Now there's one other way to write this circle, and that would be divide everything by r squared. So then it would be x squared over minus a squared, x minus a squared over r squared, plus y squared, y minus b. Oops, 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 oops. Y'all let me get away with that? That parentheses is inside, okay. The exponent's outside, over r squared. And when you divide this by r squared, that's equal to 1. So there's the other way to represent a circle. X minus a squared, or x squared, over r squared, plus y minus b squared over r squared. Notice again, the same coefficients is equal to 1. Okay. Now, you revolve that around itself, around any axis, and now what you've done is created a third dimension. Okay? And now you have the z squared involved with it as well, because now you've got not just 2 dimensions, but 3 dimensions. Now, what I was calling A and B, they're calling x0, y0, and z0. That's the center of the sphere. But the r squared, that's the same. So, doing the same thing I just did down here, you could write this over r squared, this over r squared, this over r squared, and then this would be over r squared too, so that would be equal 1. That's actually the more generic form for the equation for a sphere. Okay? Now I can't do anything with the planes. Planes are just two-dimensional things here, so they actually, it's an extension of a line. A line in two space would be, there's several ways you could express it. AX plus BY plus C, let's make it plus D, is equal to 0. In other words, you might recognize this better as something like AX plus BY is equal to C, okay? Or something like that. That's any line in the plane, right? All your exponents are 1 here. So to get it into space, you add a third dimension, a Z. But it's still in space, and now it's on a plane. That represents a line. A line is one-dimensional, the plane is two-dimensional. In space, you add a third dimension, and now this takes up a plane in space. Okay? Now, rather than writing the out here like I did this, you can subtract this from both sides and basically have that same form. Okay? So that's a plane. Everything is the first power. Okay? Your x, y, and z are always the first power. All right. Now, a third type of surface in space is called a cylindrical surface, or simply a cylinder. But when I say and think cylinder, I think of the same thing you did, a tin can. Okay? But it doesn't have to be. That's a right circular cylinder. Any cylindrical surface or cylinder, here's the definition for it. To define a cylinder, consider there's our familiar right circular cylinder. Now this one doesn't have a fixed height. There's nothing that says it's fixed. But here's how we express it. It's any intersection of it is a circle. X squared plus y squared is equal to a squared. That was our equation for a circle, remember? Where a was the radius, and that's what the radius is here. Now this is centered at the origin, right? But the difference is, this is three-dimensional, so everything z can go any value at all, but always x squared plus y squared is equal to a squared or r squared. That means you're always got that radius going up and down. Circular base, radius a or r, but now since it's allowed to be in 3 dimensions, z can be infinitely high, infinitely low. The rulings are parallel to the z-axis. Now, I don't know for sure what they mean by the rulings, unless they mean this line here, that line there. Those are all parallel to the z-axis. Now, that cylinder was generated by a vertical line moving around the circle, x squared plus y squared equals a squared, where a is the radius that's in the plane, and any vertical line that runs around that forms a cylinder. Those lines go infinitely high or low, so that forms the right circular cylinder. They don't necessarily are tin cans because they don't have tops and bottoms. They go infinitely in space. Right circular cylinder. Okay? Now, obviously, you don't have to be right. If this was a circular cylinder that went at an angle like that, that would be a circular cylinder, but wouldn't be right. Or if this cylinder was elliptical rather than circular, that would be okay. For instance, this thing is neither elliptical or whatever, but that's a cylinder. Yours is circular, but it changes its radius as you go up. So anything like that is a cylinder. Okay? Actually, these two probably would be less so than other. This circle is called the generating curve for the cylinder, as indicated by this definition. The definition of a cylinder, let C be a curve. Okay? Now that curve doesn't need to be a circle. Any old curve. In a plane, and let L be a line not in a parallel plane. In other words, if if this is a plane and you've drawn your generating curve there, whatever that curve is, then L can't be in a plane here. That would be parallel to it. L has to be some other line, not in a parallel plane. Then the set of all lines parallel to that L, they could be at an angle or they could be right, it doesn't matter. And the intersecting circle is called the cylinder. So let's just take this curve right here. Weird curve, that curve right here. This is from a biology class, okay? And if you took any line and then every line parallel to that through that curve, that's a cylinder. It's not circular, it's not even closed. Okay, now if you took that whole thing, that would be closed. But yeah, if you just took this part here, that would be it. Or this curve right here. If you took any line and then did all the lines parallel to that, that would be a cylinder. It doesn't have to be closed. Okay? They don't have to be right. Okay? They can be anything that's not parallel. The curve is called the generating curve. Also, another name for it is directress, very seldom used, but you could use it, of a cylinder. The parallel lines are the rulings. That's why I said the parallel lines were that. On that last one, that was the ruling. That was one line, then all the lines parallel that go through that curve, that forms the cylinder. Okay? Now, without loss of generality, you can assume that C lies in one of the three coordinate planes. It doesn't have to be some plane out in space. So it's either the X, okay. Now how I usually refer to that as the x-axis, this is the y-axis, and this is the z-axis here. So this would be the xz plane, the yz plane, and the xy plane. Okay? So without loss of generality, we can assume that C lies in one of those planes. So let's say it's in the YZ plane, this plane right here where the board is. And if we drew this curve here on this board, and then did any lines parallel and followed along the curve, these are your rulings, anything parallel to that would follow the curve, that's a cylinder. Doesn't have to be closed. Just any surface that follows that curve. Okay? Moreover, this text, what we're going to do, we're going to restrict our discussion to right circle, but right cylinder. So we're not going to have these weird angles. We're going to have them perpendicular to the board. That makes it easier to think about and deal with. Cylinders whose rulings are perpendicular to the coordinate plane containing the curve C. Note that the rulings intersect C and are parallel to whatever line L you choose as your first ruling. All the others intersect C and are parallel to that line. That's the generating curve, and these are the various rulings that define the cylinder. Notice they're infinite in these dimensions. You don't have to have them fixed, cut off. They usually just cut them somewhere, but they're usually infinite. Because lines are infinite in general. Unless you talk about a line segment, then that would be okay. All right. For the right circular cylinder shown in figure 11.6, the equation of the generator, okay, that's the first one we saw. That one, okay. Let's see. Yeah, 11.56, okay. Then the generating curve was this closed circle. X squared plus y squared equals a squared. That circle is centered at the origin, because there's no numbers after this, and of radius a. Okay? To find the equation of the cylinder, notice you use that same equation if it's right circular, right cylinder. Note that you generate any one of the rulings by fixing the values for x and y, then allowing z to take on all real values that we define that go along that circle. So that's what forms your right circular cylinder. Okay? In this sense, the value of z is arbitrary and is therefore not included. So the equation for the cylinder is exactly the equation for the curve. You just have to say this is two-dimensional. The cylinder would be three-dimensional. Any value z you want to attach that fits that curve. Okay? In other words, the equation of the cylinder is simply the equation of the generating curve. That's what I just said. So the equations of cylinder, the equation of a cylinder whose ruling are parallel to one of the coordinate axes contains only variables corresponding to the other two axes. So if the one is parallel to the z-axis, if this, no, I'm sorry, this is the x-axis this way, this is the yz plane, so all the things parallel to the x-axis that fit that curve would be like this. Now we've said they're all going to be right cylinders, so it's going to be good. So that would be a right circular cylinder. So the equation of the cylinder whose rulings are parallel to one of the coordinate axes contains only the variables corresponding to the other two. Well, if this were x and y, like I just said, then that circle would be on the floor down here, but it would be at the origin. So you'd only see a part of it down here, if that's my z-axis, a part of it here, and then it would go up and down from there. Okay. So, sketch the surface represented by each equation. Now, unfortunately, we're sketching on 2 dimensions, trying to sketch something 3-dimensional. So it's not an easy task, okay? So I'm going to do the best I can here. Don't worry, you're not going to be required to do too many of these, okay? But let's draw a 3-dimensional set of axes here, and I don't do this well, okay? We'll call this the x-axis, this the y-axis, and that the z-axis. And by the way, do you know why that's the case? You use the right-hand rule. If you take your right hand and point your fingers in the direction of the x-axis and then bend them to the direction of the y-axis, this is positive z. So positive x, positive y, positive z. So you see this fits. And that's why this line, that line, and this line fit a right-hand rule. Okay. So here's the best we got. Z is equal to y squared. Okay. Well, there's z up there and there's y. So that's this one. That's going to be, okay, the minus z would be going down here, minus y would be going out here, and minus x is going out here. Okay? Trying to make it look like 3 dimensions, but this is only a 2-dimensional graph. So z is equal to y squared. So if y is plus, okay, we know the origin is on that, because when y is equal to 0, z is equal to 0. Okay? Then when y is equal to 1, or minus 1, z is 1. 1 in both cases. Okay? So basically, this is your parabola. I may not have it drawn quite right. Okay? And this is on the YZ plane, the plane that's with the board there. So if you're, you draw, and the x-axis actually is one of those, goodness, I keep forgetting what they call those, rulings. The x-axis is one of the rulings because it's on the plane. Okay? So, but also the axis parallel to x-axis here, parallel to the x-axis here, parallel to the x-axis here, you know, parallel to the x-axis back here. All that sheet that you would have that goes along here, along there, and up there, that would be your cylinder represented by. Not closed. It's an open cylinder, and all of them are perpendicular. Okay? Now, you draw it in the plane that the 2 variables are, and then you make it parallel to the one that's not. Now, my picture really stinks. They're not really parallel, but get over it. Okay. And what I'm going to try to do is erase all my ugly drawing here. Okay? But keep my axes. And they're pretty lousy axes at that. Okay. Let's do the B part. Okay, the B part is z is equal to sine of x. Okay? Well, here's the z plane, there's the x plane, so that's the plane that's going like this. XZ plane. Okay? Now, x is the independent variable. When x is 0, z 0, so there we're back at the origin again. And when x goes up to pi halves, z goes to 1. And when it, oops, I'm going the wrong direction. Yeah, I always do this, or quite often if I don't catch myself. positive x is out this way, okay? So that would go up to okay? Basically, your sine curve on that axis, on that plane, the the xz plane, and then your cylinder would be perpendicular to that, perpendicular to the y-axis. So the y-axis is actually one of those rulings, okay? I keep forgetting the word. And then everything parallel to the y-axis as you go through that. So it goes up and down and up and down and up and down. So it's a sheet that does this, basically making a wave. I can't draw it, but you get the general idea of what it is. Okay? Going through that curve parallel to the y-axis. Okay? That's the B part. We'll see a picture of it later. Oh, yeah. Oh, no. Sorry. This is only between 0 and 2 pi, so it's none of these back here. I'm sorry, I didn't read the whole problem. It's none of these back here. Okay? It's only the ones this way. And it would stop right. Oops! Yuck! I forgot to turn off my eraser. Okay. Okay. So that would be stop right there. So it would be, as you follow that curve, down, up, and back down again. That would be the sheet that goes through here. Okay, coming out this way. All right. Now, let me erase my ugly drawing, and we'll see how they drew them. Okay. The first one is the graph is a cylinder whose generating curve is a parabola in the YZ plane. Okay, now they drew their axes differently from mine. The X is almost the same place. They drew the Y this way. This is more of an isometric orientation. And then the Z's up here. So in the YZ plane, there's your parabola. The generating parabola is this one. As you come out of Y or back in Y, the Z's go up from there, from the origin. So then you take your lines parallel to the x-axis, and they go like this. There's one of those, and they go like this. And the y-axis is actually one as well. There's your cylinder. Not closed. Now this shows a limited x, but there's nothing in here that limits x. So it goes infinitely in both directions, all along x. Okay? Positive x and negative x. Make sense? Okay. Then the B one is like this. The graph is a cylinder generated by a sine curve in the XZ plane, but only going from the origin. And again, the x is here, the y is there, z is there. So you start here, you go up. At pi, it goes to 0 and down to -1 and up to 0 again. And it's this sheet that makes the pi wave there. Okay. Now it goes infinitely in these directions. Y is actually one of those. I always forget that word. Rulings. Okay, Y is a ruling. It's just a strange word. And this red line right here is a ruling. Okay, all those rulings that go like that. That's the cylinder. Same equation as the generating curve. Okay, it's just this is three-dimensional. That the generating curve is two-dimensional. Okay. Finally, we get to quadrant surfaces. And can't remember your name, but you asked the question, what is a quadrant surface? There it is. So remind me of your name. Matthew. Got it. Okay. So here's the answer. The fourth basic type of surface, so we have spheres, planes, and cylinders. The fourth type is the quadrant surface. Now, where they get the term quadrant, I'm not absolutely certain, but here's what I think. If I say quadratic equation, what comes to mind? Quadratic equation. Could you give me a quadratic equation? We just had at least one. There was a quadratic equation right there. At least one of the exponents is squared. The maximum exponent is squared. That's a quadratic equation. So a quadric surface, the maximum exponent, but now you're in 3 dimensions. When you say surface, you deal with 3 dimensions. The maximum exponent is 2. They don't all have to be 2, but the maximum exponent is 2. Now, I don't know if that's where they get their name, but that's where I think. Relate back to quadratic equation, quadric surface, maximum exponent of 2. Okay? Quadric surfaces are 3-dimensional analogs to the conic sections. What in the world is a conic section? Does anyone remember? We've not had it in the calculus sequence yet, but you may have run into it before. Let me see if I can get some clear space to write. Conic comes from the term cone. And a cone is something that basically you get 2 intersecting lines and revolve them about here. So you have, that's a cone. You think of ice cream cone. That's what I like to think of. Or if you're in chemistry class, you're filtrating cones. You know, those are cones, okay? Now, actually, cones always are positive and negative, okay? So that's your cone, okay? How you intersect that cone determines what kind of shape you have. Now, these are revolved around, so if these are parallel to the plane that goes through that point, perpendicular to that, then these are circles. And a circle is a conic. Goodness, what do they just call them? Conic section. A circle is a conic section. But if you tilted that a little bit, then you have an ellipse, right? That's a conic section. Okay? If you take a plane and cut down like this, then the conic section you get there is a parabola. That's a conic section. If you take a plane that's perpendicular to the axis of that and cut, then you get a shape here and a shape up here, and that's a hyperbola. So those are your 4 basic conic sections. Circles, ellipses, parabolas, and hyperbolas. Those are your conic sections. So those are 2-dimensional structures, okay? Your 3-dimensional extension of that are your quadric surfaces. Quadric meaning they have squares in them. And certainly circles and others have squares too, but these are 3-dimensional. Okay. So these are the 3-dimensional analogs to the conic sections. Circles, ellipses, parabolas, hyperbolas. I left off the other one, the obvious one, the cone. The cone itself is a conic surface, okay? Because there you just cut right down the middle of it and you have a cone, okay? So, the equation for the quadric surfaces in space is a second degree, notice I said just like a quadratic equation, second degree equation, but this time in 3 variables. That makes it a surface. 2 variables, we have a conic section in 2 dimensions, 3 variables, then you have a quadric surface. Now here is the most complicated of all these. Some ax squared plus by squared. Now immediately when you see the a's and b's are different numbers, that means it's not circular, okay? And c is yet a different number, c z squared. But then you have d times x times y plus e times x times z, f times y times z, g times x alone, h times y alone, zi times z alone, and then some constant j. You've covered them all. Those are all the possible terms you can get in a quadric surfaces. Don't worry, we're not going to do this, okay? Now, here's the 6 basic types of quadratic surfaces. Ellipsoid, which comes from ellipse. Hyperboloid of 1 sheet, which we'll talk about this later. Hyperboloid of 2 sheets. Okay, we'll talk about that later. Elliptic cone, elliptic paraboloid, and hyperbolic paraboloid. So you take your shapes and you combine 2. This is purely ellipsoid, and we'll talk about why. Every trace of this is an ellipse. Hyperboloid of 1 sheet, 1 trace will be a hyperbola, okay? Other traces may be other things. Hyperboloid of 2 sheets, same deal, but this takes 1 sheet, this takes 2. We'll see what the difference is later. Elliptic cone, that's just the cone we just talked about, only this time it's not circular, it's an elliptic cone. An elliptic parabola, meaning a paraboloid, in one dimension you have an ellipse, and the other dimensions you have parabolas. We'll talk about that. And then a hyperbolic parabola, in one dimension you have hyperbolas, in another dimension you have parabolas. You'll see where the names come from later. Notice we aren't really using our circles because circles are basically a special case of an ellipse. An ellipse, the 2 axes are different. A circle, they're the same. So we don't even mention, actually a circular ellipsoid would be a sphere, but we've already talked about spheres, so we're not going there. Okay. Now, here's where we're going to differ a little bit. Okay. If you have these cross terms in them, if this is your z-axis, your x-axis, and your y-axis, if you have the cross-section, these shapes are at some weird angle. That's why you have the cross terms. We're not going to deal with any of those. They'll mention them, but that's all. Okay? What these linear terms do, make sure I say this right. I think they move your center around, okay? And that's all they do. And what the J does, it could also, it's just a number to make things come out okay, to fix the dimension, okay? So, what we're going to get to next is this. The intersection of a surface with a plane is called the trace of the surface. Okay? It's a thing to remember. The intersection of a surface with a plane is called the trace of a surface. We're going to deal with planes that are parallel to one of the axial, the XY plane, YZ plane, XZ plane. Okay? To visualize a surface in space, it's helpful to determine the traces of some well-chosen planes, and that's what's going to tell us what kind of surface we have. The traces of a quadratic surfaces are your conics. They can be circles, hyperbolas, ellipses, and parabolas, okay? Together with the standard form of the equation of each of the quadratic surfaces. They're shown in this table. Now, I think what you'll see here is we are going to keep everything right. We're not going to have them tilted, so you don't have the cross terms. We're going to just have the simple terms. Okay? So, here's the first of these. This is an ellipsoid. If you were to do a trace of this, that's a plane parallel to the XY plane, the XZ plane, or the YZ plane, any trace you do is going to form an ellipse. Okay? You do a trace here, that's an ellipse. A trace here, that's an ellipse. A trace here, that's an ellipse. They're all ellipses, that's why it's called an ellipsoid. The trace parallel to the XY plane are all going to be ellipses. Parallel to the XZ plane are all going to be ellipses. Do a trace, do a plane through there, it makes an ellipse. Parallel to the YZ plane, any one you do parallel there is going to trace to an ellipse. That's why it's called an ellipsoid. And notice the form here. X squared over A squared plus Y squared over B squared plus Z squared over C squared is equal to 1. That's why I went back and wrote my sphere dividing by r squared. If this were a sphere, A, B, and C would all be the same. That would be your r, and we make it r squared. Okay? If they're different, that's an ellipsoid. Now, two of these could be the same, and the third different. That would be an ellipsoid. All three the same. It's still an ellipsoid, but we call that one a sphere. But they all three can be different. But they're equal to 1. So that's sort of your standard form for these quadratic surfaces where you can do it. Now, not always you can do it, but now if you take those that are on the xy plane, okay, the surface is a sphere when, here's what I just said, A is equal to B is equal to C, and none of them are equal to 0, of course. Okay? Because you can't ever divide by 0. Okay? But if they're not equal, then this is an ellipsoid. A sphere is just a special case of ellipsoid. Now here is the xy trace. That's where on the xy plane, that forms an ellipse. The yz plane, that forms an ellipse. And the xz plane, that forms an ellipse. Yz plane, that forms an ellipse. Now how do you get these? Set z equals 0, and there's your ellipse. By the way, I guess I meant to do this. I usually do it and I forgot. Okay, let me back up. And I mentioned circles, right? Let me give you the standard form for all of your conic sections. I meant to do this earlier. A circle, and I'm going to write it in the form that we do. This is x squared over a squared plus y squared over a squared is equal to 1. We did that one before. Those two have to be the same. I usually put r squareds there rather than a squared. An ellipse as a conic section is x squared over a squared plus y squared over b squared is equal to 1. That's an ellipse. Two-dimensional structure in ellipse. In this case, the a and b don't have to be the same. If they are the same, it goes back to being a circle. If they're not the same, it's an ellipse. A hyperbola is x squared over a squared minus y squared over b squared is equal to 1. Okay? Those are going to be things that go in opposite directions. Okay? Opening outward. They look sort of like parabolae, but they're not. Okay? And your parabola is going to be, I'll write it the way we normally do. Y is equal to x squared would be the most generic form of that. Okay, but it could be x is equal to y squared or any of the other. Okay, or the other way you could write that is x squared, and you could put over a squared minus y over b is equal to, let's see, is that equal to 1 or is it equal? No, that's equal to 0. Okay, because you're moving it to the other side. So that is your generic form of a parabola. Subtract the y from both sides, and you could introduce coefficients if you wanted to, but when you subtract from both sides, you wind up with a 0. So anytime you have a paraboloid, you're going to have something that's equal to 0, not equal to 1. The others, your things, when you write them in these forms, will be equal to 1. Okay, I meant to tell you that before, so let's go back. And now you see what I was going to say before. If z is taken out of the picture and you're only in the xy plane, you have an ellipse. That was exactly the form of an ellipse. Take y out of the picture, and that's an ellipse. Take x out of the picture, that's an ellipse. So that's why it's an ellipsoid. Any trace that you do where you eliminate one variable or do something parallel to the elimination of that one variable, you form ellipses. Okay. Now here's a hyperboloid of one sheet. Okay? In the xy plane alone, a trace in the xy plane or perpendicular to the xy plane, where z is out of the picture, you have an ellipse. That was just like your ellipse up here, okay? Look at this. When you go parallel to the z-axis, you get these ellipses, okay? Could be circular if A and B are the same, but generally they're not the same, so they're ellipses, okay? But if you eliminate the x, then your trace is a hyperbola. Eliminate the y, your trace is a hyperbola. So this is hyperboloid of one sheet. Now what makes it one sheet is the fact that here's one way to tell. One way. Okay. Well, this. Okay. There's only one complete curve around here. That's what makes it one sheet. But at value z equals 0, let's see if this is right. Yeah. You can have a value of z is equal to 0. You have an ellipse there. When you see two sheets, you'll see that's not the case. But it's hard to do without doing the two sheets first. That's a hyperboloid of one sheet. One trace is an ellipse, just like before, but the other two traces are hyperbolas, like this or like this. Okay. See, here's one set of hyperbolas here. There's the other set there. No, this is one set. This is yours. Okay. Now, notice how it looks. Hyperboloid of one sheet. Your basic setup, you have one plus and one minus. Okay. Here's the hyperboloid of two sheets. This one, you have one plus and two minuses. Now they happen to put the plus as the z, so that means, and here's what I was getting at before. If you had, let's see. Well, let's just leave it like this. One plus and two minus. So that's the easiest way to tell. That's going to be our hyperboloid of two sheets. Now, what do we have now? If you did a cross-section of this, you'd have x, okay, and move these to the other side. Take the z out of it, move these to the other side. That makes this a minus 1, okay? So it'd be x squared over a squared plus y squared over b squared, or just change signs to both sides, is equal to a negative 1. Well, guess what? That's never going to happen, is it? Because this is going to be, so at z is equals 0, that can't happen because you don't have any value in here, okay? Because this would always be negative, that's always positive, okay? It can't happen, so z cannot be 0. But z can be some value positive or negative, and when you get up there, then your trace are ellipses, just like they were before. Okay? So the trace parallel to the xy plane, when it intersects, those are ellipses. But there's an area in there where they don't intersect. Okay? So you'll have a blank space in there. That's what makes it two sheets. Okay? But your other two traces, if x is 0, then that's a hyperbola here or here. Okay? If y is 0. Both of those are hyperbolas. This one would make a parabola, make ellipses, but only with z some positive or negative value greater than the sum of those two. Okay, so that's why there's a gap in the middle. Now here's your elliptic cone. That original conic section, the xy traces are all ellipses. Now this is sort of tougher. Oh, well, let's first take a look at it, okay? What's different here, this looks just like your your hyperboloid of one sheet, except of one sheet there's a 1 there, and your elliptic cone is a 0 there. Okay? What does that mean for you? Okay? For some value, z, if you move this to the other side, then you have x squared plus x squared over a squared plus y squared over b squared is equal to some value. For any fixed value there, then that would be ellipses. Okay? For every z, you have a different ellipse. But when you do, say, x equals 0, that would be here, they say, and this is where I have problems with it, you have, okay, not equal to 0, not equal to 0, but anything outside of that, then you have your hyperbolas going down, which is your conic section, okay? And the same thing here. When you cut a plane parallel to the xz plane, it's ellipses, or yz plane, I mean not ellipses, hyperbolas, you get both of those. Same as you did, that's how we first defined it, okay? So you can't be on this plane, you have to be some distance away, because this has to move over there and allow yourself places where that would be. So you have ellipse when you do your traces this way, hyperbolas when you go this way or that way. So that looks a lot like this, except this one goes through the origin, this one does not. Okay? These are not particularly easy to see. We really don't do too much with this one. Okay? We do that. Now, an elliptic paraboloid. Now, parabola means that any trace is going to be a parabola parallel to this axis or that axis. Why it's elliptic paraboloid? Because the trace this way is going to be an ellipse. Okay? So therefore, if z is 0, or z is any number other than 0, that is going to be an ellipse. Okay? If y is 0, then that's a parabola this way, right, this way, and when x is 0, it's a parabola that way. So that's an elliptic paraboloid. Ellipse this way, paraboloid the other two ways. Paraboloid the other two ways. It's just like the parabola spun around an axis. Okay? Now the hyperbolic paraboloid is strange. Okay? Now this one, it's z is equal to x squared plus y, x over a squared. So you basically, the equation of an ellipse here, as long as this is any number other than 0, positive number other than 0. So you see you don't have any negative z's here. Okay? So it's always opening upward. Okay? Now, and then you cover either one of those and you have parabolas in both dimensions. Now this one's a bit strange. It's just like that, except there's a minus sign here. So when z is any number other than 0, okay, at 0 it's going to be 0. Okay, but any number other than 0, whether positive or negative, really, then you get hyperbole. Okay, so z like this trace here, you get one coming out this way and one going that way. Traces like this, you have going, no, that's not the right one. But traces along the y-axis, okay, these are going to be parabolas. Oh, parabola this way and parabola this way. This way they're going up, this way they're scooping down, okay? On the y-axis they're going up, like most parabolas do. The YZ plane, they're doing like this, and the XZ plane, this is curving down. Okay, so those are like that. But when this is anything other than 0, any number other than 0, then you have hyperbole this way or that way. Okay, and actually going up like this, you also have hyperbole. It's sort of hard to see that way, but that's what it is. The axis of the parabola corresponds to the variable raised to the first power. That's the axis this way. What sometimes this is called is a saddle point, because it sort of looks like a saddle. You drag that over a horse, you sit in the middle, okay? So that's called a saddle point. So those, to answer your question, these are your quadratic surfaces. The traces correspond to your various conic sections, either hyperbola, parabola, ellipses, occasionally a circle, okay? Now, they say classify and sketch the surface. Now, here is how I would suggest you do this. Remember, on most of these surfaces, let's go back and look, that one, you isolate the variable, and you don't have any constants in it. There, you isolate the variable. So the two paraboloids, you isolate the variable to the first power, okay? But if you have a constant, there it's +1, there it's 0, there it's +1, there it's +1, okay? So therefore, if you have a constant, get it by itself. But you want it to be positive. So what I would suggest you do here is say 12z squared, no, I'm sorry, did it backwards. Okay. I did the wrong one. Okay. Take this negative, move it to the other side. I don't have my pen. Okay, here we go. 3y squared, we move that to that side, and we move the other two, minus 4x squared, minus 12z squared is equal to, leave this on this side, 12. Okay? So we moved all those to that side and left this by itself. And then I'll reverse the signs. Okay? So it becomes a plus here, a minus there, and then move that to the other side, leaving it plus. So you move that to that side, so you have this one positive and that one positive. These two become negative. Then rewrite it. Now, divide by 12, because you want to be the 1 over here. Divide by 12, divide by 12, divide by 12, and divide by 12. So what do we have? Y squared over 4, or you could call it 2 squared if you wanted to. Okay? This one's a little messier. X squared minus x squared over 3, which would be the square root of 3 squared, if you wanted to write it that way, minus z squared over 1 squared, that's 1, and that's equal to 1. Okay? That's now your standard form. A 1 here and everything else with denominators here. Okay? So what would this one be? Well, let's see what would happen if you try to eliminate the y. You get to an impossible situation. A minus can't equal a positive. So this should be a clue there, but we'll come back to that in a minute. Eliminate this one. So you can't really eliminate this one, but if you let this be a number that you subtract, subtract the 1 from here and move these two over here, then you have, when you move both of these, those are both positive, and that forms an ellipse, and you have this thing minus 1. Well, as long as this thing is greater than 1, okay, you have an ellipse on this side, and you have, if you eliminate this, you have a hyperbola. Eliminate that, you have a hyperbola. So this is a elliptic hyperbola of 2 sheets, because you have a gap here that you do this minus 1. Anytime this is less than 1, you have no answer. But when it's greater than 1, you have a value. That would be it. So that has the same form of that one. See, z squared minus x squared over a, z squared over c squared minus x squared over a. Okay, the difference here, everything looks the same. The difference here is the axis of this is the y-axis, and the other things is z. So if you go back here, this thing would be out, or this one would be out here, this one would be out here. So that would be exactly the same form, just with the axis being the y-axis. Okay, we're getting close, folks. All right. Classify and sketch the surface. The sketching part, that's a real pain in the neck. So let me try to x, y, and z. Okay. Now we've got to have y greater than 2. Right? Because if y is less than 2, when you subtract the 1, you're going to have a negative number. You can't have that. So you have to have y greater than 2 or less than minus 2. Okay? So 1, 2, 1, 2. Okay? So this then becomes your ellipses going like this. So it's, get out of there. Okay. It's going to be there and there. Okay? Where these are your ellipses going around like that. So there is your elliptic paraboloid, no, elliptic hyperboloid of 2 sheets. So the classification is elliptic paraboloid, no, hyperboloid. I keep saying it wrong. Hyperboloid. Goodness, I can't write. Boloid of 2 sheets. Okay? Elliptic hyperboloid, because you have ellipses on these traces, and you have hyperbole on the traces this way and that way. Hyperboloids are both of those. So it's elliptic hyperboloid of 2 sheets. Actually, rather than doing traces, it's easier for me to see this way. When you do it this way, as long as you subtract the 1 from here, move over there, then you have to have this greater than 2. This has to be greater than, this term here has to be greater than 1, meaning y has to be greater than 2. Because 2 squared over 2 squared would be 1. Anything greater than that. So from 2 on, then you get your shape. That gives you ellipses here, but then go back to this form. That's hyperbola. That's not hyperbola. Okay? So that's a elliptic hyperboloid of 2 sheets because they're separated.
Would that be y squared over 4 squared? Or
Say that again.
would that be y squared over 4 squared?
No, okay. This would be, when you divide this, that would be 1 over 4, right? So that would be 1 over 2 squared. 4 is 2 squared. Yeah. And this would be 1 over 3, but to get a square down here, you have to do the square root of 3 to make it 3. And then this would be 1 over 1, with 1 square root of 20. So that gives you your dimensions on those axes. I didn't bother to try to get those. I can't draw my things that well. All right. Does that make sense? Let's see how they do it. I think it'll be similar to what I did, but let's see. He said, begin by writing the equation in standard form. There's the original equation. They subtract. Oh boy, what a weird way to do this. what they do is divide everything by 12, by minus 12. What a weird way to do this, okay? But that works, okay? And then, and they put this minus down here, this minus here, that minus there. It doesn't matter, it works, okay? And then rearrange, moving the 1 to the other side, and then you have the positive term first, and then these two, okay? Now, that to me is not quite standard form. That's why I wrote it 2 squared, square root of 3 squared, and 1 squared. That to me would be standard form, okay? You can conclude that the surface is a hyperboloid of 2 sheets with y as the axis. The positive is along with the axis. And why it's 2 sheets is that if you move this to the other side, subtract this here, then that becomes an ellipse, but only when this thing is greater than y. So that means y is greater than 2. It has to be greater than 2, meaning you have a gap in there that you can't have it. So that's what makes it 2 sheets. And the xy trace there is a hyperbola. The xz trace is no trace. You have no place where y is equal to 0, because this is positive, that's positive, and you get a negative answer there. Can't happen. Cannot happen. Okay? And then your yz trace, that gives you another hyperbola. But if you do anything beyond your y squared over 4, anything that is greater than, y is greater than 2 or less than negative 2, then you do get ellipses, because that's what you would get there. And this is how it looks. Here's your vertices, you might call it plus 2 and minus 2, and then you get hyperboles this way and that way, and ellipses when you're beyond 2, you get there. So it's elliptic hyperboloid of 2 sheets. Here they just say hyperboloid of 2 sheets. I think the better word is elliptic hyperboloid of 2 sheets. All right. Now, they're skipping example 3, but I have a feeling if we try to do example 3, we're going to run out of time, aren't we? Okay. So we'll pick up with example 3 next time. Oh, and that's where my mark is already. So we will go with that. All right. Good deal, folks. Homework exercise. I knew y'all wanted that. You were starting to go without it, didn't you? Okay, I think you can do 5 through 10. I only have the answers for the odds in the back, but you should be able to do all of 5 through 10. Okay? The answers for 5 through 9, the odds are in the back, and you can also find them at calcchat.com. I mentioned that before. Okay, then do either 11 or 13. They're both at CalcChat. 11's at CalcView. And then try to do any of the odds 15 through 25. They're all at CalcChat. 17's at CalcView. Okay, we'll leave that alone and pick up the rest of those later. And if any of those you can't do, we're going to be doing a few more examples of those before we come back. When we come back. Oh, and the good news, next week we actually have 2 classes. Not just classes on Wednesday. We'll have classes on Monday and Wednesday. First time of the term, right? So we'll have classes Monday and Wednesday of next week. What did you do to your leg?
I heard it playing softball. It's
Did you?
meniscus.
And what?
I'm meniscus. I'm meniscus.
Can't hear.
Meniscus. It's like a part of the knee.
Oh, I see. Okay, I'm sorry. I can't hear well. My hearing is terrible. Okay. Let me show